Well, we have reached a very important point in this class about distance protection. Because right now, what we want to discuss is the distance protection apply to three-phase transmission lines. Okay, that is what we want to discuss at this moment. And at this moment, I would like to start my discussion saying that when we are working with three-phase systems, all my power system analysis students, they must remember that we have symmetrical faults, but also we have asymmetrical faults, okay? What I want to that you understand is if we are working with three-phase systems, we have at least 10 different types of faults, tuned faults. You must remember we have three-phase faults that represent symmetrical faults, and in reality there are two of them. I mean, three-phase that is not connected to ground, or ABC, and then we have the three-phase fault connected to ground, and that is ABC to ground, okay? But also we have three combinations of two-phase faults. Then we have three combinations of phase to ground faults. And finally, we have three more combinations of double phase to ground faults, okay? What I'm trying to say is there is a big number of possible combinations of faults, okay? And what we want is to install relays, distance relay at the transmission line, that they must be able to identify those faults and also be able to identify the fault and um, produce a signal that open the circuit breaker and isolate the fault, okay? On the right hand side here, what you can see is, okay, if we are working in a three-phase transmission line, we need signals, voltage signal and current signals, and we need at least three of them for voltage and three of them for currents, okay? And that is when we have at least three current transformer and three voltage transformer, okay? The signals coming from those transformers, they must be arranged, and then we will supply those voltage and current signals to the relays, number of relays that we need to do in order to appropriately identify the faults, the 10 different faults, okay? What I'm trying to say is that we need to identify the appropriate connection between voltage and current transformer, and this topic was explained in the class related to CT and VT. And then we need to identify for those relays specific settings for the distance, but these settings are basically based on the total positive impedance of the line, okay? And this must be done for any fault condition. At the end, we will need six measurement units, I mean CT and VT, and also we will need a number of impedance uh, or distance relay, okay? Now what I will do is the following. I would like to do a very important discussion, theoretical discussion about the implication of having distance protection on a three-phase line when there are some faults, okay? And I would like to start this discussion with one of the faults, and that is the line-to-line fault, okay? Imagine that we have the three-phase system that we are showing over there on the left-hand side, and that is a three-phase circuit, and we have three CTs and three VT, okay? But what is important is that we are inserting over there a shunt fault between B and C. Okay, and during these conditions, of course, we need to assess what is the behavior of the system in terms of impedance, because remember, the distance relay will work basically based on the impedance. Okay, well, all my students must remember from my classes of short circuit analysis that using symmetrical components, this beautiful theory created by Sharp-Fortescue in 1918, using symmetrical components, you must remember there is a zero, positive, and negative sequence, okay? If we are working with a line-to-line fault, all my students must remember that the zero sequence is not included because there is not contact with the neutral or ground point during the fault. And the positive and negative sequence, they must be connected in parallel as I am showing over here, okay? The next step is, okay, we can use a single equivalent model over there to represent, you can see here the positive sequence, and here you can see the negative sequence. And I believe all of you can see that using circuit analysis, mainly Kirchhoff voltage law around the loop, because here you have a single loop. You can have a loop starting from here, go there, then go to the top, then going back and come back again. That is the loop, okay? If we apply that loop, we can obtain this equation over here, Kirchhoff voltage law equation, relating the voltage at the positive sequence voltage at the relay location and the negative voltage at the relay location. And that voltage is related to the positive sequence impedance of the transmission line and the negative sequence, okay? If we assume that the positive and negative sequence, they are equal, and that is a quite typical assumption for three-phase transmission lines, well, we can calculate over here, and this is that is the definition of the positive, that is the positive sequence impedance that the relay is measuring, okay? ZL over there, as you can see, is the ratio between the sum of the positive and negative voltage and divide by the difference of positive and negative current at the relay location. And in this case, what we are getting over there is the ratio between voltages and current that define impedance, okay? What we want to do now is, okay, I love the symmetrical components, but in real life, I am working with phases A, B, C, okay? For that reason, all my students must remember from symmetrical components, you must realize that the ABC vector is equal to the matrix A. The ABC vector is equal to the matrix A multiplied by the symmetrical components. And from there, we can do few mathematical tricks that we already did in power system. And what I am getting here is, okay, if I divide the voltage difference between the phase B and C at the relay location between the difference between the current B and C, we obtain what's supposed to be the positive sequence impedance that this relay sees when there is a line-to-line fault, okay? What is the main conclusion here? What you need to understand is that when we have a line-to-line fault, the impedance, the apparent impedance that the relays see, depend on the difference between voltage B and C and the difference between the currents B and C, okay? Okay, and let's try now to understand what is happening in a three-phase line when there is a double line to ground fault, okay? It's the same situation. We have the same transmission line, but now phase B and C, we are connecting together and going to ground. And we are assuming that this is a bolted B to C ground fault, okay? That means there is not impedance, okay? Well, from symmetrical component, my power system analysis student must remember that positive sequence network, negative sequence network, and zero sequence network, all of them must be interconnected in parallel, okay? In this slide, I am showing again the positive the positive sequence network, the negative sequence network, and the zero sequence network. Okay. Again, using some symmetrical component properties, what you need to understand, what you need to see is that the impedance, the positive impedance that the relay is watching or see is depend on the difference between positive and negative sequence, or in terms of phase B and C, the difference between voltage B and C and the currents B and C, okay? Finally, what I want to show you is what's happened if there is a line to ground fault, okay? If there is a line to ground fault, a line to ground fault, in this case, we consider that the phase is, of course, on phase A. Now what we need to do is, okay, for a line to neutral fault, all my students coming from power system analysis, you must remember that the three sequence networks, they must be interconnected in series, okay? Series connection for of the positive, negative, and zero sequence, okay? And that is what I am showing you over here, okay? Of course, if you are having three sequence networks in series, of course, the sequence currents are the same, okay? And here, what I am showing is the detail for the positive sequence, negative sequence, and zero sequence. Subscript R represent the voltage at the relay location, and the subscript R over here represent the current at the relay location, okay? What I will do now is something very simple, okay? Um, using Kirchhoff voltage law, this voltage plus this voltage should be equal to the voltage over here plus this voltage drop plus this voltage drop. That is this first equation. However, you must realize that when you sum the zero sequence, the positive sequence, and the negative sequence of the voltage at the location relay, what you get is the voltage of phase A of your location at the relay location, okay? Then what we did is, okay, let's substitute this here. That is what I am doing. What I am doing is substituting here from here to there. And that is the reason for this here, okay? And then what I am doing is, okay, let me do a basic trick here. And the basic trick here is, let me add and decrease, let me sum and reduce by this term, okay? That is a mathematical trick, and that trick allow me to identify a relationship between what is the voltage on phase A, what is the voltage at phase A, and here you can see this is the apparent impedance that the relay is C when there is a single line to ground fault, okay? What I want to do is something very simple. What I want to do is the following. That expression over here, you have here the phase current, phase A current, but here also you have the zero sequence current, okay? What I want to do is just use more symmetrical components and do a very interesting trick here, okay? What I want to do is the following. You must remember that the zero sequence current is equal to the sum of ABC divided by 3. You must remember that, okay? And the sum of ABC is what we call in the protection wall the residual current, okay? If the system is working in a three-phase load and is a symmetrical load, the residual current must be 0, okay? But if we have an unbalanced condition like the single phase fault, the sum of those three currents is not 0. And that is what we call the residual current, okay? What I am doing here is something very simple. What I am doing here is I want to eliminate from this equation the zero current. And what I will do is using the new introduced definition of the residual current and put inside the equation. And what I can get is a beautiful, beautiful expression, okay? Equation number three is telling me, that when there is a line to neutral fault, the impedance that the relay see is the ratio between the voltage at the location of the relay divided by the short circuit current and this important term over here that is relating positive and zero sequence plus the residual current, okay? Okay, that expression is extremely important because in this case, I don't know if you realize, but one of the problems over here is that in this equation, the impedance is appearing in both sides of the expression, okay? And that create a bit of misunderstanding, okay? What we can do here is try to simplify the equation making few assumptions. For instance, a typical assumption is creating a relationship or defining a relationship between the zero component and the positive component. For three-phase transmission lines, typically the transmission line impedance, the zero sequence impedance of one transmission line is between 2.5 and 3 times the positive sequence, okay? Of course, the exact relationship depend of the real configuration, geometry, and some other parameters. Okay. However, in this class we can make an assumption. The assumption is very simple, and we will assume that the zero sequence is equal to three times the positive sequence, okay? If we do that supposition, that assumption here, well, that will simplify this term over here, and the positive sequence will disappear. And right now we are creating a simplified version of the impedance that is looking into the relay. However, this assumption is key component. We don't want to keep this assumption because that assumption there are many transmission lines that we don't follow these 3 times the positive sequence. Okay, what I want to do now is, instead of simplifying this, what I will do is the following. The impedance that the relay can see from the location is equal to the voltage at the location of the relay divided by the current on phase A. But now I will use 2 important things. One important thing is I will introduce the factor K. And the factor K will take in account the real relationship between positive and negative sequence, okay? Sorry, positive and zero sequence. What I'm trying to say is this term over here, K, is what we know the residual current compensation factor, okay? And what this factor is doing is considering the relationship between positive and zero sequence at the transmission line, and at the same time this value is multiplying the residual current, and that is this term over here. Let me clean a bit the whiteboard. This term over here is the most important term, because this term is compensating the fact that we are having a single line to ground fault in a transmission and in a three-phase transmission system. Okay, what you need to understand is that term, that is the residual current compensation factor. The residual current compensation factor depend of the zero sequence, the positive sequence impedance of the transmission line. Okay? Okay, but now what we need to understand is that we can then set distance relay protections. Now we can set distance relay protections, and these settings will be specifically for line to ground faults, okay? And what will be the settings? Well, the settings will be defined. The settings will be defined by the voltage at the relay location, phase A, B, and C, and then we will use, instead of using the short circuit current, we need to compensate the short circuit current, including the K factor that define the ratio between positive and negative and zero sequence, okay? The interesting thing is, in the majority of the transmission line, the factor K is between 1.5 and 2.5 times, okay? And in the average case is typical 2.0, and that corresponds to the assumption that the relationship between the zero sequence impedance and the positive sequence impedance is 3 times. Okay,